This is Mrs. O'Neill for AP Chemistry, Chapter 8, Section 5, Drawing Lewis Structures. So your objective is to apply that Lewis structures are a powerful way of predicting bonding patterns and to understand the concept of this formal charge that is going to help us identify the most dominant Lewis structure when a compound has multiple structures that are plausible. So pause the video, again read as you write, and make sure you're understanding the rules of how to draw these structures. So I'm not going to go through this step by step because the next slide gives us the steps to writing Lewis structures, and then we're going to go through many examples. But just real quick, you're going to sum up those valence electrons. You're going to connect everything with single bonds. Hopefully everybody gets an octet with the exception of hydrogen. We want to remember that our central atom, or the atom that we're going to put in the middle of our structure, is going to be the least electronegative, and that means it's going to be the farthest away from fluorine. If there's any leftover electrons, we're going to put them on the central atom, and we're going to use multiple bonds if there's not enough bonds or not enough electrons to go around to make that octet. So this is a useful equation when we're dealing with just the bonds between the atoms, but this does not work for exceptions. So again, we're going to use this equation as a checkpoint. So again, write out your steps to drawing Lewis structures, and then we're going to do an example. And these are 2 checkpoints. So let's look at an example of CO2. So you can either listen to the video and pause and write as you go along, or you can listen to the whole thing and then pause and write what you want, or you can listen to the whole thing, pause, and do whatever you need to do, and then rewind as well if you want to re-listen to it. So anyways, this is CO2, and most of you probably already understand or know the structure of CO2, but one of the reasons why I'm showing it to you is because you know what the structure is, but how did it get there, right? So it's always nice to look back at something that you already know, but know how you got there. So now you can do structures of molecules that you're unfamiliar with. So this is one you are familiar with. So again, I'm going to go through this kind of quickly. Count up those valence electrons. How many carbons do we have? How many oxygens do we have? Again, look at their group numbers, right? Their group numbers are going to give us those valence electrons. So hopefully that information makes sense to you. And 16 valence electrons is our goal. In other words, that's how much we really have to deal with. We only have 16 valence electrons to deal with the bonding process. So now let's draw our structure. Again, we're going to deal with carbon first, and carbon is farther away from fluorine than oxygen, so that's going to be our quote-unquote central atom. We're going to have oxygens around it. Now let's have everything have an octet except for hydrogen, but we're not dealing with hydrogen. So these are all the electrons we have if everybody has an octet. So now let's count those actual electrons up. 7 plus 6 plus 7 gives us 20. Uh-oh, that's more than the 16 that we really have available, right? So the valence electrons are what we have available, but if we have everybody having an octet, we really have actually 20 electrons. So we got a couple more electrons. So what are we going to do? Well, read number 3b, because our actual electrons are greater than the valence electrons. And this is really where it's important. We're going to erase a lone pair from both atoms that we're going to make the multiple bond in between. What does that mean? Here we go. So we're going to erase the oxygen, a pair of electrons, and make a single dot. We're going to now erase a pair of electrons from the carbon and make a single dot. Now, why do we do it that way? Again, because it tells us we're erasing a lone pair from both of the atoms where we're making that multiple bond in between. Okay, so now let's count up our electrons that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Uh-oh, we have more electrons. So we have still more electrons than the valence that we really can have, or that we need to get to. Our goal is 16. So we're going to do the same thing. Cross off a lone pair, make a dot for our electron that's going to be shared between that carbon and oxygen. Again, erase a lone pair from both atoms, so we need to do it for the oxygen as well, and make that dot. So now let's count up these electrons. If we erase those pairs of electrons to make those multiples, we end up getting the 16 valence electrons that we really want. Okay, so again, at this point, make sure you're writing some information down in your notes in some way to understand where those double bonds came from. So again, just as checkpoint, 16 minus 16, right? We had 16 valence, we had 16 actual now that we made those double bonds, so our overall charge is 0. Now, this is a neutral compound. There's no charge, so we should have 0, so that's our checkpoint. That makes sense. However, if we had a polyatomic ion with a -1 or a -2 charge, we would do the same calculations, but now our overall charge of that polyatomic ion should match the charge of that polyatomic ion. Hopefully that makes sense. Now let's look at this, happy minus have. Well, if however many, I should say 8 times 3 for all those atoms, minus the 4 for carbon and the 6 for the 2 oxygens, gives us 24 minus 16 divided by 2. This gives us a number of 4. So 4 bonds between the atoms, okay? So it's not 4 bonds all over the place, it's 4 bonds between the atoms. So this should make sense. We have 2 bonds here between the oxygen and carbon, 2 bonds here between the carbon and oxygen, so we have 4 total. Again, this works nicely with any structures that don't have any exceptions to the rule. So here's some more examples. I'm going to kind of click away. It is up to you if you want to pause and try to do them yourself and do checkpoints, or do you want to just kind of listen and kind of click along and see if that makes sense, and then do the practice problems as well. It is up to you. Now, if you are really struggling, let me also suggest you can also Google how to draw the Lewis structure for almost all of these, if you need a better or a more explanation as to how to do them. So number 1, again, I'm just going to mention a few things here and there. Carbon is the least electronegative, so that gets the central, as well as it should kind of make sense that if you have 4 chlorines, they probably kind of go around the carbon or around the other element that's there. Count up those electrons, put those electrons, everybody's got an octet, you match up those electrons, you are done. You can also draw it this way with the bonds as lines and not dots, and that's okay. But a reminder, those extra lone pairs of electrons better be on there. Almost every AP exam I've seen, they want to see all the electrons that you're using to make that structure. This one I want to mention that you have that negative, so keep that in mind. Your overall charge is -1. So hopefully that makes sense, and you can also write it this way with brackets. Sometimes you see a polyatomic ion with brackets because of that charge. These are called resonance structure. Now I know it looks like the same molecule just kind of spinning around, but technically this double bond resonance structure really just deals with double bonds or triple bond compounds. This is really on oxygen number 1, oxygen number 2, and oxygen number 3. And these negatives and positive here that you see are going to be called formal charges, which we're going to talk about in a moment. Now this one has hydrogen, so remember the rule about the duet, right? The hydrogen only has 2 electrons with it, and usually the hydrogens are at the ends of the molecule. That's a big hint too. So hopefully that makes sense. Again, make sure that you're using those lone pairs of electrons and showing them. Ooh, now look at this. What does this mean? This means that it's what kind of functional group or what kind of compound? Hopefully you come to mind. Alcohol. You might want to go back to chapter 24 if you need a refresher. Okay, again, pause, see if you can do these on your own, and then I'm going to kind of click through. Remember, see if you can figure out which ones of these, hint, 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 probably the ones that have double bonds, might have resonance structure. And at this point, if you have questions, I would either put a star or a question mark or something, so when you come to class, you can either ask a classmate or you can ask me as to why these answers are the way they are. This one is the one that has resonance structures. And again, we're going to talk about these formal charges. Because the formal charges here are 0 and everybody has an octet, that's actually going to be your most plausible one. Again, we'll get to that in a moment. Again, resonance structure, just like you saw before, the double bond on this oxygen would be 1, 2, and 3. So technically, these are 3 different compounds. So here again, we have resonance structures. If we look at all of these, they all have 10 electrons that you need. And ooh, this one has a 0, 0 formal charge, so you would think it's this one, but not all of the elements have an octet. So really, this one is going to be the most plausible, but it really looks funny, doesn't it? Because we have oxygen having the +1 charge. But again, we'll talk about that in a moment. Can you come up with the functional group of this guy? Hopefully you came up with carboxylic acid. So pause the video again, fill in your blanks. So what is formal charge? Again, read over this and then we're going to do some examples. So this is really important to understand. Formal charge is as if everybody had the same electronegativity, which we know is not the case. So that's why these are not the oxidation numbers. This is formal charge to help us predict which structure would be the most plausible. Hopefully that makes sense to you, and if it doesn't, hopefully if that makes sense to you, and if it doesn't, this should. This is what's really, really useful. This is what I call the formal charge formula. I'm going to take my valence electrons, I'm going to subtract the electrons that are assigned to that atom, and I'm going to subtract them. You might see these formulas as well, but this is the easiest that I've seen over the years. So let's do an example. Again, play the video or rewind, whatever you need to do in order to understand the material. So here's ozone. Here's our structure. Now, how do we find the formal charges? Well, oh, I'm sorry. We needed to have that double bond. I apologize. So now let's calculate the formal charge. So first thing is first, valence electrons, oxygens all have 6. Now let's look at all of the bonds or all the electrons. So around this oxygen, that's how many electrons are going to be assigned to it. That's how many electrons are going to be assigned to it, and that's how many electrons are going to be assigned to it. So we're going to take the number that's assigned to it. So now remember, the bonds in those 2 notes that you just wrote, the bonds really are half the bonds go to this guy and half the electrons go to that guy. So that's where those numbers come from. And again, if you have questions, please ask in class. So we're going to do our subtraction, and that's our formal charge. So I don't know what else to tell you except the formal charge is going to help us right now. Number 2, formaldehyde really has 3 possible structures. So pause the video and see if you can come up with the 3 possible structures. Hopefully you came up with something like this, but we need to have some double bonds there. Okay, so now that we have everything that we need, our 3 structures, let's come up with formal charges. So come up with the valence electrons that each of those atoms have, and then come up with how many electrons are assigned, and then do your subtraction. So hopefully you got these numbers. Now, out of these 3 structures, which one is probably going to be the most useful or the most important? Well, I see a structure here that have all zeros, so I'm going to pick that one. I'm not even looking at the other ones. So that one will be the most plausible. Okay, they all satisfy the octet rule, so that's going to be the most important. So try to come up with your 3 Lewis structures for N2O, and again, I even give you the order of the structures. Hopefully you came up with this. Now, which one's the most important? Again, pause, come up with the formal charges for all 3. So if these are our formal charges, I'm going to quickly glance at this and go, well, this is the only structure that has a 2. Everybody else has 0 or 1, so I'm not going to even deal with that one at all. Now if I look at A and B, however, what's going to be different? Well, look at this oxygen. This oxygen has 0, but this oxygen is a -1. And between oxygen and nitrogen, oxygen is more electronegative, so the oxygen should have that negative charge. So bada bing, bada boom, letter B is going to be the most important because of that oxygen, or the more electronegative atom, has that negative charge. So again, if you want to pause and look this over just to hopefully understand again resonance structure and which one would be valid or not valid. Give it some thought. Hopefully you came up with this as an answer. All right, so again, we'll see you in class, and hopefully if things don't make sense, you have me or other students to ask questions, and of course we'll do some book work to help along as well.